what is this about? So the Ternary-Goldbach problem, also called the 3' problem, tells us, so it comes from the correspondence between Euler and Goldbach. So they were firing each other questions back and forth, but essentially the conjectures that they came up with fall into two. There's the Ternary-Goldbach conjecture, which tells you that every odd number should be the sum of 3 primes. Back then, 1 was still a prime, so nowadays we would say every odd number starting with 7 is the sum of 3 primes. And then there's the binary conjecture, which states that every even number should be the sum of 2 primes, this starting with 4. Very well. So in the 19th century, almost nothing was done. Some people strangely credited one of the conjectures to Waring, who came up with one of the conjectures later. It was verified up to 10 to the 6 by hand or so, I think. But really work started for real in the 20th century. So Hard and Littlewood showed that the theorem is true, or the Ternary-Goldbach conjecture is true, starting at a certain integer n, provided that you assume the generalized Riemann hypothesis. So that was a wonderful application of their method, the circle method. And Vinogradov stunned quite a lot of people when he showed that you could remove the generalized Riemann hypothesis. And that was really a big jump. As you will see, he really had to analyze exponential sums combinatorially to an extent that was unknown before. Very well. So what are some other lines of attack? So Schnirelmann showed in the 30s that every integer is the sum of at most k prime numbers, where k is some constant. So k got made explicit by Klimov. It was quite large at first, but then it has been reduced many times. So the last two values are 6 for even numbers and 5 for odd numbers. So of course, the even Goldbach conjecture amounts to 2 and the odd one to 3. So, well, in particular, yes. The best value would be 3. All right, so what about this? What about we assume the generalized Riemann hypothesis? Then Dzyujev, Ingeter, Ilya, and Zinoviev proved that indeed the conjecture is true for all odd numbers, if you assume GRH. So the open problem was to prove the Ternary-Goldbach conjecture for all odd numbers without assuming GRH. So what was known? So as I said, Vinogradov had proved this for all odd numbers larger than a constant C. How large was C? So there's a mistake there. First of all, Borodzin should be Borodskin. I've been told that his name is very hard to find, but it's almost certainly Borodskin. And he may have got it in 39, but he certainly did not publish the value until the 50s. So at any rate, it was quite large. Then this got reduced a couple of times. So Chen there is the same Chen as in another result towards binary Goldbach, namely Chen Jingrun. And then the best value known for C was 2 times 10 to the 1346. Well, so you might ask, why don't we just check by computer the first 10 to the 1000? You would not ask that. For a very good reason, namely, well, even 10 to 100 would not be any good, even with parallel computer, because even if you made the entire universe into a parallel computer, you have that the number of subatomic particles is 10 to the 80, making the task of checking the first 10 to the 100 cases a little bit difficult. So how far had people verified things? So, well, again, it's not just Oliveira and Silva. There are 2 other people I should add there. But they verified that every even number up to 4 times 10 to the 18 is the sum of 3 prime numbers. No, sum of 2 prime numbers, excuse me. And using that, you can actually go quite a bit further on the ternary front without that much effort. So, in fact, just using some results on prime gaps, for example, using a paper by Gamaret, you get to 10 to the 27. But if you are willing to do a bit of extra computing, adding that to the heavy computing done by Oliveira, Silva, and collaborators, you get up to 8 times 10 to the 30. In fact, you can get further, but this was not the main computing task. So the problem is that, of course, 10 to the 30, and I hope to make this an official part of mathematical vocabulary, Zoot. Zoot, this is much smaller than 10 to the 1,346. So your task is to redefine 1,346 so that it becomes 30, right? So we really have to make the constant much smaller. We have to make the math much better. So computers get up to 10 to the 30. Now it's our task as mathematicians to make the bound so sharp that this is brought up down to 10 to the 30. So Zoot means darn, by the way. Very well. So what is this circle method, which most of you are already familiar with? So we're talking about exponential sums. We're here, of course, lambda. So E is just shorthand for e to the 2 pi I. Lambda fed is just von Mangold, but look at the funny thing. So Harding Littlewood were contemporary mathematicians. They were using a very nice smoothing. They were using an exponential smoothing. Whereas with Vinogradov, well, he had his reasons. In part, it is that in the part where he really made great progress, the smoothing doesn't matter that much. But in other ways, his sharp truncation, it's a bit like lost technology with the fall of the Roman Empire. I think this was a step backwards. Sorry, Vinogradov, but so you know how concrete was lost after the Romans for many hundreds of years. Nowadays we get told to always smooth, and applied people never forgot that, but we forgot that. At any rate, so the crucial identity is just this, which essentially just means that why on earth would we use Fourier analysis to solve the ternary Goldbach problem, just because sums are, well, we're talking about a convolution, and of course the transform of a convolution is a product of transforms. So that's what you do. You have to examine this, which is just, so I don't get any magical laser pointer. But how do I do that? Very well. All right. Aha, I'm powerful now. Yes. What happened? So the solution to your problem is this, which is just a Fourier transform of the product or the cube of a Fourier transform S. So you have to examine this transform, this integral. You have to evaluate what it is. You have to show that it's bigger than 0. And for that matter, not tiny. So the contribution cannot come entirely from non-trivial prime powers. All right. So again, this must be all news to most of you. You are going to split the circle into major and minor arcs. Major arcs being, as our name indicates, really, really small. Well, of course, what happens is that they make the major contribution, or they should. Well, the reason why the binary Goldbach problem does not get treated this way is that that isn't the case there. The major arcs no longer make the major contributions, but here they do. So you split the circle into these arcs, and the arcs which are around the rationals with small denominator, you call major, and the ones with larger denominator, you call minor. So the boundary between the two was set before at the power of log, for the most part. We will go back to that later and see what needs to be changed. But at any rate, the idea is that you have the major arcs. You want to do an estimation for major arcs, M, big M for major, and you want to get, well, you're happy enough with an upper bound for minor arcs. And if your upper bound for minor arcs is smaller than your estimation, your lower bound for major arcs, and you win. The total has to be non-zero. And for that matter, non-tiny. So how do you estimate things over the major arcs? So, this means that you need to estimate S alpha x, the exponential sum, the Fourier transform, if you wish, of the primes, for alpha near a rational of small height, that is, of small denominator. So, of course, you do that with, you do that with L functions. Why? Because you can express your exponential sum as eta in terms of these twisted exponential sums. Well, why would you ever express a non-twisted exponential sum as a linear combination of twisted exponential sums? Because your angle alpha now has become simplified. Instead of being a divided by q plus something small, now it's just something small. It's delta over x. So you have this tiny phase, delta over x. Of course, n is going to get to be of size about x. So this phase will have a non-trivial effect. But it will really, it will rotate slowly. There is a sum where the phase will change slowly. In fact, it will go around the circle a bounded number of times. And that really makes life a lot easier. You know? So you can use L functions directly to estimate this sort of sum. How do you do that? Well, you estimate it using an explicit formula. So it's not as in popular accounts say in Davenport, you first derive a formula for primes in arithmetic progressions, and then you estimate your exponential sums using that. That's not really efficient. It's much better to estimate these twisted sums directly using an explicit formula. So the term within brackets appears only when the character is trivial. There's the little error, the small error that comes from the trivial zeros, and then there is this main sum over zeros. So the main term appears only for principal things. Rho goes over all the non-trivial zeros, which are in the critical band and which are believed to be on the critical line. And then F delta is just a Mellin transform of eta times E delta t. So it's eta, the smoothing, whatever smoothing you are using, multiplied by E of delta t. So of course this can be, as in Vinogradov, a non-smoothing, as in just the characteristic function of a large interval. But in that case, the Mellin transform has horrible decay properties. If you use Vinogradov's eta, meaning the characteristic function of an interval, then F delta does decrease as your imaginary part goes to infinity, but it decreases like 1 over the imaginary part, and that's really, really slow. So the Mellin transform, I remind you, is basically just a Laplace transform, which is basically just a Fourier transform. So it's analytic on a band. Other than that, you are pretty much free to choose whatever eta you want. But you want an eta such that f will decay rapidly. Why? We will see that in a minute. But essentially, you want the rows with large imaginary part to make a tiny contribution, simply because the rows with large imaginary part are harder to control. So where are these rows? As you all know, they are believed to lie on the critical line, on the line with, yes, with real part 1/2. But we know much less. We know things, we have results of two kinds. One of them is just zero-free regions. So there are these hourglass shapes where the zeros are known to lie. And there, well, we have an explicit C, and it's not too bad. But it's still, it's not that great either. And there are zero-free regions which are better in theory, but not in practice. So Vinogradov's zero-free regions, if you're doing anything explicit, they are not usable in our days. They start becoming better than the classical zero-free region very, very, very high up. So what can you do? Well, so Vinogradov and most people following him had to just use the classical zero-free region. Vinogradov himself never got to use his own zero-free region in this context. And before Hart and Littlewood were assuming GRH. Do we have an alternative to one of the two? Well, what we can also do is, for a given chi, we can verify GRH up to a given constant height. And we can do that rigorously nowadays. Well, Riemann was Riemann doing it rigorously? He was doing it very slowly because he was doing it by hand and just for the Riemann zeta function. But he was doing it. All right, so the only trick here is that I could really delve into the details here. This is not really my part of things. Well, we'll talk more about that later. But let us say that most modern methods descend from what Turing did on the subject, though there are many contributions from other people as well. You can read that up in Edwards, though he doesn't go into what Turing did. But the point is that the only catch is that you can do this only for, not just for a bounded height, but for a bounded number of chi's, because you have to do each chi separately. All right. So, well, if you want to prove the ternary-Goldbach conjecture, then zero-free regions are too weak. The only way to approach the problem is really to use the second strategy. So how much do we know? So for the Riemann zeta function, as I said, Riemann was the first one who checked some zeros, but then the best zeta, so people have gone up to, yes, a bit over 10 to the 11. Then not everybody necessarily believes this, 10 to the 12. In particular, I mean, there are several issues there. It's not just Venedivsky. With Venedivsky, you already have that he did not use interval arithmetic. But other than that, he was very careful. But here, there are some issues. So the strongest, fully rigorous result, I would say, not that I'm putting down anybody, is that of Platt, who stopped a bit before Venedivsky, but he really used interval arithmetic and some double checking and so on. Just in case this isn't completely familiar, what is interval arithmetic? Interval arithmetic is the following. To be honest, a computer can never deal with an irrational number. And in fact, even though it can deal with rational numbers in general, most of the time when you program it, it doesn't. It just knows rational numbers whose denominator is a power of 2. Those are the only things it can actually deal with. And so if you want to be completely honest, you don't deal with reals, you deal with intervals in which your real is contained. So you are speaking about a real number, but all you can manipulate is an interval, a very short interval, a comma b containing it. And then instead of asking for sign of your real, you ask, well, computer, can you give me another interval you can deal with denominators a power of 2, that contains the interval sign of interval a comma b. So if you really want to deal with real numbers rigorously, that's something you have to do, among other things. So Platt uses interval arithmetic. And if you're clever like he is and like other people are, you can actually trick the hardware to do part of your work for that. So it doesn't take forever. So what about Dirichlet functions? So already Platt had gone up in his thesis, David Platt, and we will hear of him more in the future. He had gone up to conductor 10 to the 5, and he had checked things up to height 10 to the 8 over Q. So, well, now he has gone up to, so I basically had to go all over France and beg for computer time. We were given at the end, suddenly, so we were scrounging computer time. At the end, we got more than we needed, but we managed, so he got, once we got proper computing time, he got pretty quickly up to 2 times 10 to the 5 and 4 times 10 to the 5 for Q even. And T, like here, is essentially inversely proportional to Q, because that's what I needed. Oh, well, so this is somewhat tailored to my needs, though it goes a bit further. So this is of general applicability. It's just the height that is somewhat tailored to my needs. All right, so what do we have to do? I recall that we have to get to bound this sum over all zeros rho, where, well, rho, yeah, it will have imaginary, it will have real part 1/2 up to the point where we check it, because the check tells us that in fact the Riemann hypothesis is true up to that point. No surprises there. Now, the number of zeros up to t, you would not need to check it by computer because there are very good estimations. You can if you want. But so what remains is to estimate f delta. And so what you want is that f delta of rho should be very small when the imaginary part of rho is large. Why? Because as soon as we get over the level t at which we can check up to which we check the Riemann hypothesis, we know nothing or almost nothing. We know the zero-free region, but it's so weak as to be useless for t so large. So the only way to control the contribution of the terms with rho with large imaginary part is for f delta of rho to be already very small. In other words, we have to choose the smoothing so that f delta of rho decreases very rapidly when the imaginary part t of rho goes to infinity. And we also would like it to be a nice formula, of course. All right, so what about the Hardy-Littlewood smoothing? Already that is very nice, because then the Mellin transform is just this. And how does this decrease? So this decreases exponentially. However, yes, so exponentially is great, right? But there's a coefficient in front of the t, which is basically, so when delta is smaller than 1, the coefficient is constant, essentially. But when delta gets bigger than 1, it gets to be like 1 over 2 pi delta. This is not so good, because this means, so as I said before, delta is not large, but delta, you are not going to be able to bound it by something better than a large constant. And already that will be a progress. So something that decreases, like e to the minus t over 2 pi delta, is not so great. As we will see later, we have to deal with things like, you always have to check things up to height at least roughly 2 pi delta anyhow, but you would like to be able to stop the check at, say, 5 times 2 pi delta, or at most 10 times 2 pi delta. And e to the minus 10 is not such a tiny number, unfortunately. Not if it's being multiplied by other things. So, all right, a bit of English shot into the slide. So instead of e to the minus t, you use a, so I decided at the end, last year, to use a Gaussian smoothing. So what happens then? Well, so the smoothing, the Mellin transform of just the untwisted Gaussian is just the gamma function scaled down. But since you do have a twist of the form E of delta t, the Mellin transform becomes something that is very well known, mostly not to us, but to applied people, but not as nice as a gamma function. It's what's called a parabolic cylinder function. So there had been estimates in the literature, in particular some very nice work in the 60s by Olver, who passed away a few months ago. However, even Olver's work was not fully explicit. He managed to get bounds that were tied up to a constant, but he did not specify the constant. And also, applied people actually have some applied people, you would think it would be the other way around, but when they say a closed expression, they mean something vaguer than we, as in they have series with array functions in them, and those are not so nice to deal with. And in fact, these are not even convergent series. They deal with series that are convergent in the sense of Poincaré, and we also don't want that. So we want to get some bounds, not necessarily that tight, but bounds that are useful and where everything is completely explicit. So in this case, the only thing I could do was to prove them myself. So, well, that's a spin-off, if you wish. I hope it will be used outside number theory, though it will be improved quickly, I'm sure. But what do you get? What you get is, well, what you get is precisely what you would guess if you applied the method of stationary phase on the back of an envelope. And that's the reason why I chose the Gaussian to begin with, because the method of stationary phase was telling me that the answer would be nice. What is the answer? The answer is that when delta is small, meaning smaller than 1, say, then you do get an exponential decay. Yes, slightly worse than what you had before, but still very, very good, much better than what you need, in fact. E to the minus pi over 4 times tau. And what happens when delta is large? Yes, you will need to check things up to 2 pi delta and a bit further, but the decay is no longer exponential, it's Gaussian. It's much, much faster than exponential. Yes, this is large. Sorry, petit got redefined as large here. Yes, that's since I'm giving the talk in English, I can define French to mean whatever I want it to mean. I redefined it. Yes, I know. Yes. No, this should be yes, delta grand. Very well. All right. Yes. So for delta large. For delta grand, this should be e to the minus 1 over 2 times the square of the ratio. So even if this is, say, 10, if this is 10, this is tiny. And even if the ratio here is 6 or 7, this is already very, very small. So there's always a trade-off. So why is there a trade-off? It's Schrödinger. I have no idea who, so people in physics in the larger world think this is a theorem in physics. Well, physics does not have theorems, but it's a theorem in mathematics, that it's a series of theorems, and it was known by some people before Schrödinger, that you cannot have a function that decreases very rapidly. Sorry? Sorry, Heisenberg, yes, excuse me. But Schrödinger's cat, no. At any rate, Heisenberg, yes, I'm very sorry. All right, the point is that, as people will let you know, you cannot, no, it's not, all right, the cat is a secondary issue. The point is that you cannot hope for a function that decays as fast as you could hope for, and whose Fourier transform also decays as fast as you could hope for. So the cat issue usually gets expressed as you cannot have a compactly supported function whose Fourier transform is also compactly supported, but in fact it gets a bit worse. You cannot have something that decays faster than exponentially and whose Fourier transform, or whose Mellin transform for that matter, decays faster than exponentially. However, you can have something that decays exponentially and whose Mellin transform decays much faster than exponentially. That you can have, and that's what I do. So you just have to, and the trade-off is very tiny. The trade-off is, well, it's a trade-off in the constant, but for this application, this is more than allowable. So instead of pi over 2, we have pi over 4 here, and what do we win by that small sacrifice? We win the fact that we have much faster than exponential decay here, in a range that is much more sensitive. All right, so in that way, we get estimations not just for the Gaussian, but also for any other choice of smoothing function that consists of the Gaussian times any smoothing function that is quote-unquote band-limited. To use, again, an expression from a field I don't know, namely to use the expression that engineers use. So band-limited just means something whose Fourier transform, or in this case, whose Mellin transform, is compactly supported. In fact, you could use either. I ended up using something whose Mellin transform is compactly supported. This will just delay the decay by a little bit, by a constant. Not by much. All right, so this works out nicely. Any smoothing function like this will give you very good major arc estimations. Aha, but for which major arcs? Yes, it will give you very good major arc estimations for delta and q bounded by a large constant. But yes, bounded by a constant. Beyond that, this will not work out. If you wanted your delta not to be bounded by a constant, you could not use these verifications of ERH up to a finite height. And if you wanted your Q not to be bounded by a constant, you also could not use these verifications because you are allowed to check things only up to a bounded conductor, because you are allowed to check only a finite number of chi's. So these forces are major arcs to be few in number. You are allowed to have only a constant number of major arcs of constant over x weight. So all the rest of the circle, if you follow this strategy, will have to consist of minor arcs. So this method works very nicely for few and narrow, for major arcs that are narrow and few. But it does make the rest of your tasks much more difficult, at least qualitatively speaking. So a writer in Science News, I think, said that this was trading Emmental cheese for Münster cheese because the holes got smaller. At any case, you have to get better at the rest of the cheese. So you have to give much better bounds for the minor arcs. After you do that, you no longer need to worry because then the major arc bounds will be very good. They will take a lot and a lot of work, but they will be very good. And that's what I did in the second paper. But so what about minor arcs? Well, so first of all, before I said eta, but in fact we could use 3 different smoothing functions. I'm going to use 2 different smoothing functions. So how do you evaluate the contribution of the minor arcs? Well, the most brutal way is to just bound it by an L2 norm squared by times an L infinity norm. And bounding an L2 norm is easy, and in fact you cannot do better than the truth. The truth is easy to determine by Plancherel. So we have to bound just the S infinity norm, the L infinity norm of S. Well, in fact, doing that would not be enough, because this would give you, say that you bound this by, well, given how big the cheese that is left over after the holes is, you're not going to be able to give a bound that is better than a constant. That is better than a tiny constant times x. And the L2 norm introduces a log. So if you just had this, you would lose. So you need to win that log back. This is a recurrent motif. In many places, it looks like we're losing a log, and then we have to fight hard to get it back. This game is not about improving constants. This game is about winning back logs. And if you fail to win a single log that you ought to win, you lose. You're out of the game. So how do you win that log? There are essentially two ways. So there's a way that I used in the first version that is based on unpublished work by Heathrow. But then there's a better way based on work by Ramaret. But in either case, you are replacing x log x by x log q. The idea is that you can try to bound the L infinity norm not over the entire circle or over the entire minor arcs, but on the intermediate region. So you bound things for arcs centered on rationals whose denominator is larger than something and smaller than something. And the bounds will be worst when you are actually in the region that used to be major and is now minor, that is the arcs around medium-sized denominators. But those you can show, and this is what you can do using Heathrow or Ramaret, those you can show give a small part of the L2 norm. Not a tiny part, it will be about a constant times x, but a small part. And the bigger your denominators get, the bigger the contribution to the L2 norm will be in total, but the smaller the L infinity norm on those arcs will be. And it's just partial summation. What you do, you take advantage of that using partial summation. So nothing very sophisticated. The important part is to bound the L2 norm on these intermediate regions, going from denominator R0 to denominator R1. All right. So, but how do you bound things for the minor arcs? And also, given that we're allowed to use different weight functions, which weight function do you use for the minor arcs? So you need to use something. No, I'm not redefining major. What happens is that, so there are these etas, and only one eta will be relevant for the minor arcs, but all etas are relevant for the major arcs because you have to compute the integral over the cube in the major arcs. So very soon, using using things by Heathrow and Ramaret, two of the etas just go home in the case of the minor arcs, but all etas are relevant for the major arcs. So all etas have to be good for the major arcs. So the Merlin transform has to decrease exponentially, and in fact better than exponentially for delta large. That you have. At the same time, why did Vinogradov ever use a sharp truncation? Because combinatorially it's easier. It's not the easiest choice, but it's nice to work with. And Tao, when he was doing 5 primes, he was choosing something that was not too different. It was a bit smoother than Vinogradov's choice, but not that much. It was the multiplicative convolution of the characteristic function of an interval with itself. So there are two technical improvements here. One is that the thing is bounded away from 0. That's useful. But it's also that it's something like this. It's a multiplicative convolution of something times itself. Later, when we split sums by identities, this will be useful. Still, either Vinogradov's choice or Tao's choice is no good for the major arc estimation. This is good for the minor arc estimation. This is actually very convenient, but not for the major arc. So what can we do? Well, it turns out that this is a case of a political problem you can solve, in the sense that you have these two lobbies called major and minor arcs trying to make you decide what eta star should be. And in fact, you can do a very simple compromise. So say eta 0 is a kind of Merlin transform that the major arcs want, something whose eta 0 is a kind of smoothing function that the major arcs want, namely something whose Merlin transform decays quickly, and f star f is a smoothing that the minor arcs want, something simple and compactly supported. And you can just, what you do is you take the multiplicative convolution of what one side wants with what the other side wants. And that's it. Why? Because when you need to estimate S eta star on the major arcs, well, it's enough to estimate S eta 0. And that you can do in a sheet of paper. It gives you right away. If you know SF, then you know SF star G. You can get it very quickly. And also, if you know SF star F, which we will get in the minor arcs, you will also know eta star. Because the exponential sum with a smoothing that is a convolution just becomes an integral of the exponential sum for, well, one of the two things that you are convolving, your choice. You have to be a bit careful, especially in the case of the, given that one of them does not have support bounded away from 0. So that's one of the reasons why we will make the support of both be almost bounded away from 0. Here the support is bounded away from 0, but we will choose eta 0 so that it decays very quickly near the origin. It has a third order 0. That makes this integral estimation nicer. At any rate, so what can we get for the minor arc? So this was my result from last year, and it originally looked much uglier, besides being worse. Now it fits into 3 lines that are very well centered and that have just read the part that is blue. So essentially, so for x large enough, let alpha, or in fact 2 alpha, be a over q plus a small error. And then if q is not huge, you will have that the exponential sum over x is bounded by what? Well, these things are tiny, these things in black. But how do you read this? So this looks slightly scary, but in practice it's bounded by a constant. If you got very close to the limit of validity, you would get log x. But in fact, but even then the bound would be very good because you would have x to the 1 over 6 in the denominator, but in practice you don't get close to that bound. So r is bounded by a constant, in fact a constant smaller than 1. So think of a constant smaller than 1. So here you have basically just log delta 0 of q divided by delta 0 phi of q, and this is better. Why delta 0? Delta 0 is a max of 2 and delta over 4. In other words, it's never worse than 2, it's never smaller than 2. And when delta gets larger, this is an important feature, things become better. The further away you get from the center of the arc, it's not as in some previous work that things become messier and worse. The estimates actually become better. So this is, by the way, how one manages to get that one needs to check things only up to a lower height as q increases, because the major arcs can be narrower. All right. So it's essentially then log q over phi of square root of phi of q when delta 0 is small, and it's something better when delta 0 is larger. Yes, and when q is very large, then you get a power savings. Yes, and this looks frightening, but there's x to the 1/3 being saved here, so it's nothing. And as I said, r is in practice smaller than 1. Very well. All right, so what are some slightly invidious comparisons? So you gain, in practice, you just gain an order of magnitude over tau. But remember that I should say that computing time for major arcs is worse than cubic. So in fact, a gain of an order of magnitude makes the computing time improve by a factor of 1,000, which is the difference between something being realistic and not realistic. Besides there being other improvements elsewhere. All right. And how good do things have to be? So before things were a bit worse, but now, because I'm using Gamma-Geiss bounds rather than Heath-Brown's bounds, you just need the bound to be better than 1 over 2 log q for you to win. And this means that, well, that means that you just need to go up to here, up to 1.5 times 10 to the 5 for q odd, and 3 times 10 to the 5 for q even. And in fact, Dave Platt has managed to go further. As I said before, So with all of this computing time, and I should thank all the computing centers that I have thanked in the paper, including people I met here in Marseille. So with a large to moderate amount of computing time, Platt managed to go up to 2 times 10 to the 5 and 4 times 10 to the 5. So to go back to the Romans, all over the place they have tried to build like a Roman. That is, Roman ruins were built because Roman architects were not very self-confident. They knew that they could have made a little slip here and there. So they needed to leave themselves a lot of margin so the thing would stand up. And so because of that, Roman ruins still stand up, even though they weren't supposed to last that long. So I have judged it prudent, since there are many calculations done by hand by myself, to always leave myself a large margin. So here, I have been very careful, but here I'm just letting you know that computations have gone much further than what I need. All right, so this was done by Platt. All right. How much time do we have for the real math? Excellent. Very good. So people who really want to wake up for the hard part, are there such people? I'm sure. So where do the new bounds for the minor arcs come from? All right. So as I said before, really you have to hunt for qualitative improvements. So one thing is, let's go over the main points. The fact that you can obtain cancellation within Von's identity. Also the fact that, as I said before, the distance from the minor arc is our friend, not our enemy. For several reasons. So in type 1, I will talk more about type 1 and type 2 in a second. In type 1, you have that the distance from the center of the arc gets put into a Fourier transform, and the Fourier transform of something smooth decays. But you also have a different technique. I will talk more about that in a second, but let me talk about it now. The fact is that every real has excellent approximation by rationals. If you have that you're in a minor arc but not in the center, that means that the center of the arc is a good approximation to you, but not a great approximation. That is, there have to be better approximations, and you should not have to hunt that far to get them. That is, if you're at a visible distance from the center of the minor arc, once you decrease the tolerance, there has to be another approximation of not enormous denominator, close to x, but not less than x, which is better. And so you can actually make these two approximations fight against each other, or rather you can use whichever one is more convenient at each point of the estimation. You can go back and forth, and that really, really decreases error terms a lot. And this has to be of general applicability, I think. In type 2, and I will also talk more about that in a second, what you have is that this delta allows you to scatter the input to the large sieve, and I will make clear what I mean by that. But also another motive in the proof is that there is this very, very close relationship between the circle method and the large sieve. So the large sieve, you can see the large sieve from two perspectives. One, the very abstract perspective as a duality principle, but you can also see it as an approximate Plancherel identity. But that means that the large sieve is something extremely close to the circle method. They are really two sides of the same coin, and you should trade ideas back and forth between the two, and you should not see them as black boxes. So in particular, any ideas that, so there are many ideas that have been developed for the large sieve, you can put them back into the circle method. And in fact, that's part of that's how I got to apply Ramarei's ideas. So Ramarei has a better prime large sieve. So you can get those ideas and apply them to the circle method directly without going through the large sieve, strictly speaking. Because whatever works for approximate Fourier analysis generally works for just Fourier analysis. Then there are also the advantages of a smoothing eta, though that's hardly news to the audience. I mean, by now, for most of us, smooth is like brush your teeth. But still. All right, so what about Vaughan's identity? All right, so Vaughan's identity is very nice. Why is it very nice? Because it made Vinogradov proof much simpler. And you really see the type 1 terms where you have, so a type 1 term is what you have, and this is Ivanets's notation. I got infected by this notation from reading Friedlander and Ivanets 15 years ago. So this is just a truncation, as you can see. So you have that lambda is the sum of convolutions, and this is a type 1 sum because log is completely free. As in, there's no funny arithmetic thing going on there. Log is a nice smooth function, and so you will have nice, if not very long sums inside. And this is a type 2 sum because yes, because you are going to have two large things, and the free thing might be too short. So you will have to make these two large arithmetic things fight against each other in some way. And the last thing is negligible. So, well, how is Vaughan's identity a gambit, however? It's really like a gambit in chess, where you give, in fact, a romantic 19th century gambit, where you give up 2 pawns or logs in the opening. You get a lot of flexibility back as a result. You get to choose U and V, as well, however you wish, but you lose 2 logs. And in this game, you can't lose logs, meaning that if you lose them, you have to win them back before you win the game. Yes, and in fact, at least one of the logs gets recovered, and the other one log doesn't matter because of X and Y reasons. It becomes a log Q. But one of the logs gets completely destroyed, and it has to be destroyed several times because it's like the Hydra. You chop it up with Cauchy-Schwarz, and then it becomes 2 logs. And so, all right. So how do you recover these factors of log? So first of all, you are allowed to get cancellation in this sort of sum that you get from Vaughan's identity. Why wouldn't you be allowed? You wouldn't be allowed if these were a sum restricted to n congruent to a modulo q for q large, because then there would be no way to estimate it without using 0 free regions. And we are already at the range where it's not profitable to use that. However, this is a special congruence class. It's a congruence class 0. And then this reduces to something without restrictions, essentially. And then you can get bound. You can even get a very good bound. You can win a log in an elementary fashion, and you can win a second log in a non-elementary fashion. But since it uses only zeta, you get good bounds. You can also go and actually improve Vinogradov's lemmas. This has, I mean, people had improved them by constants before. You find this in the work by Debussy and Rival, which, by the way, is highly recommended reading. It was one of the things that really got me into the problem in 2006. Yes, but you can improve things further in a qualitative way. I could go into the details, but it gets a bit technical. And then you can adapt them to deal with the input from a smoothing, and then they get even better. So what about type 2 sums? Well, if you Cauchy-Schwarz sums the type 2 sum coming from Vaughan, you are going to have a sum like this. And you might think, oh, I'm going to get cancellation right away from mu. Oh, but D is really large. Oh, and D will be in a really tiny range. And then this might be very hard. But in fact, you can make this work out. And again, you are not allowed to use arithmetic averages of mu over arithmetic progressions. You are just allowed to use averages of mu period. You're allowed to use a zeta function, but nothing else. Yes, D divides M. That's right. D divides M. That's correct. Yes. Thank you. Yes, I should make a list of. All right, and also you have to, well, so that gains 1 log, but we Cauchy-Schwarz at some point, we always do. So remember the Hydra. So we have to win the other log, and that log you can win using there are all of these large sieves adapted to sequences of prime support, which as many as you know, and as some of you proved, in fact, win you back a log, and that's crucial. All right. I said before that delta helps us. So yes, that's in part because of the decay of eta hat. It's in part because of what I already explained about the alternation between A prime, Q prime, the other approximation that must exist if A over Q is not excellent. But what about type 2? What happens here is that if you have that the alpha is not quite A over Q, but there's a tiny change, it's like a photograph that is slightly out of focus. And what that means is that when you go around the circle, drawing the points at which you will apply the large sieve, and you come back to the origin, you don't get back to the same points. If alpha were exactly A over Q, you would get back to the same points, which would have these large separations between them, and it would be very nice. And the large sieve would give you very good bounds, but you would have to apply the large sieve many times, once for each time that you go around the circle. So see, the bounds from the large sieve gets multiplied by the number of times that you go around the circle. Whereas if you are slightly out of focus, and here I will draw a picture, what do you have? You have that, yes, these are the angles, the points at which you will apply the large sieve, but then you got slightly out of focus. You're here, not here. And this will be more out of focus, and so on and so on. And it will take a while before you have, I exaggerated the out of focus thing. In fact, it's only a very slight out of focus. But that's good, because it means it will take a long while, many turns of the circle, before you could risk any overlap. And so what can you do? You can have this photograph that is exposed over and over and over and over, and you give that thing to the large sieve. The bound that the large sieve will give you will not be quite as good as before, because the gaps are much smaller. You have these gaps. But the effect will be much better, because you don't have to multiply the result by anything. You're feeding many things at the same time to the large sieve. All of these angles, you're feeding it to them. Because they are slightly out of focus, you do have this separation between angles. A much smaller one, it doesn't come from 1 over Q, it comes from delta over X, but still. All right. And even that you can combine still with, with the prime support. Because what you can do is, you can go enough times that you don't remotely risk any overlap. So you have these clusters of points around the angles. So you still have some spacing between the angles. You have some tiny spacing between the angles, but you also have some tiny spacing, some not so tiny spacing between the clusters of points. And you can take advantage of that, because you can fill those up by using the fact that you have prime support. Because that's how you do things by Montgomery's lemma, say. You scatter things in the unused regions of the circle, using the fact that your prime support allows the gaps to give you some useful information. So that's what you do. These clusters get sent all over the place, and you get a log from the prime support. All right, and everything goes works well for n bigger than 10 to the 30, and in fact, in the version I just submitted, I did it for 10 to the 29. And in fact, if you don't want to work like a Roman, you can make it work starting at 10 to the 25 or so. But at any rate, we already did Platt and I the check up to 10 to the 30. In fact, 8 times 10 to the 30. So it's done. So you have that every odd number is a sum of 3 prime numbers. And that's the end of the story.
We've been asked to use the microphone for questions. Are there any questions for Harold on this tour de force involving Schrödinger's cat, Romans, and I forget what, cheese, yes. And politics, amazing.
Yes.
Questions for Harold. Adam.
Thank you. So the thing that you do on the minor arcs,
yes.
especially this L2 thing on the major minor arcs, if I
yes,
can put
yes,
it like
yes,
that, how is that related to the kind of majorant things that Bourgain does and other people do for exponential sums over primes in more additive combinatorics things? So there you might take out half of, so you have S of alpha to the 3, you might take out S of alpha to the half, you have S of alpha to the 2.5 left, and then you have an estimate for that. Is there some relation between those things?
Yes, I will have to look at that. I should say I read what Bourgain did a while ago. He generally has more sophisticated analysis, as in he never Cauchy-Schwarzes when he can use Hölder's identity instead, and so on. But I am not sure that more sophisticated analysis is going to help here. How I don't know of any major minor arc estimations for the L2 norm or things like that in his work, but it would be nice. That's actually a good idea to look at that together and see whether that can give anything. But I think his improvements are in a different direction.
Thank you. Any other questions for Harold?
Yes.
You hear me?
Yes.
Did you try to use the dispersion method rather than circle method from scratch? I mean, not in the middle of
That's
the
what
argument.
that's actually what I did. That's a very interesting question. I got interested into the problem because in 2005 I thought I had come up with an elementary a proof that is not goes through the circle method, and that yes, but that did use, of course, L functions and so on. And it used just a dispersion method and cancellation over mu. But then I was informed that Heathrow had come up with the same proof in the 80s. So, and that really there wasn't that much of an interest in skipping the circle method. And that's how I got back to the circle method. And I also realized that what I was doing, that was not using the circle method, was not going to have any hope of giving us any good constants, at least not the way I was using it. Maybe there's a better way of using the dispersion method. But that was actually the first thing I tried.
That's what we do in Rutgers.
Sorry?
That's what we do in Rutgers.
You do what?
Dispersion method.
All right.
Well, that's what happens when chicken leaves its nest.
Okay, anybody else want to slag off the circle method? Any other questions for Harold? Okay. Well, I'm sure we'd like to thank Harold again for that wonderful talk.